paradigm in computer networking, which has generated a tremendous amount of excitement in the industry as well as in academia. And we're going to talk about how to program the network, the computer network, as you know, using this new paradigm. And about the t-shirt, this is all part of a big project called Frenetic. For those of you who've been here last year, Frenetic was introduced in ICFP, so sort of ICFP is like a home for Frenetic. So that's, I mean, you can look up Frenetic, you should be able to find the work, a lot of work that's going on, both in programming language community and in networks. So let's talk about networks. Well, the traditional network is a set of, you can look at it as a set of boxes connected by network links, but these boxes are pretty much special purpose devices. Of course, there are routers, there are switches, but we also have lots of middle boxes and stuff which have, you know, millions of lines of code doing very much vendor specific stuff. Like Cisco has its own kinds of boxes, Juniper has its own kinds of boxes with its own software and so on. So what this ends up in is that you have a network which becomes very difficult to manage, and the operating such a network is also quite costly because just to pay the network operators, you end up having huge cost, and you cannot have, I mean, if you look at a data center, for example, some firms like Google and Facebook and so on, they employ a lot of effort in eliminating the costs involved in operating a network, and that is because you know, there are a lot of outages which are caused by just manual errors being done by these network operators when you know, they try to fit it with the network. So operating a network is expensive, and of course traditionally we found that the network is sort of, you know, one of the most resistant components to innovation of any kind in let's say in a data center or WAN or an enterprise network, wherever you go. So and that's of course because, you know, you have a Cisco army that is, you know, that has to be contacted for making any change to its switches to the network dominated by its switches, and you have all these vendor specific. When I say vendors, I mean Cisco, Juniper, or whoever. You know, they are the EVT. So so what SDN does is sort of try to change what is wrong with traditional network. So what I just described is summarized in the slide. That is, the problem with a traditional network is that you have all these boxes connected by these links, but they do two kinds of things, but in a very mixed up manner. The first thing is packet forwarding. That is, if a packet enters the network, or if a packet reaches a switch, the switch will forward this packet looking at a certain forwarding table that it has. That is, if the packet headers look like this, then it should be sent on this port to this part of the network or something like that. So that is packet forwarding, which is called the data plane in network terminology. And the other part is the control plane, which actually computes this forwarding table. That is, each switch or each box communicates with the other set of boxes, and they have to talk in the same language. So to get any functionality that you need on the network, you need to design a distributed protocol that all these switches have to follow. Right? So, but the point is that each of these boxes has its own, you know, strange mix of you know, control plane in the data plane. That is, Cisco has its own set of, you know, APIs that you need to program with in order to you know, let's say write a link state protocol, or you know, any function that you would want on the network. So what that ends up in is that the network operator has to do everything manually, in the sense that he has to go to let's say each and every router in some sense and change the software on the router if he wants a new functionality, right? And this is of course pretty much vendor specific, that he has to do Cisco switches in one way, and then Juniper switches in one way, and then he has to program the firewall in some other way. I mean, all these middle boxes. So when I say middle box, for those who don't know, a middle box is like a firewall, a load balancer, or an these are special purpose devices that you put in the network to get any functionality. Okay, so what SDN does, okay, this is the punchline. What SDN does, or what software-defined networking does, is migrate all the control plane functionality away from the switches into a centralized box, and that is called the controller. So a controller is pretty much, a single box which has an enormous amount of resources. What you do is that you can write an arbitrary program at this controller, and that program is going to do network monitoring, topology discovery, or if you want a firewall, you can write it as a program. So anything you want on the network, you don't have to design a protocol now. You don't have to do vendor-specific things now. All that you have to do is write pieces of software on this controller, and the controller, or you can, for example, you can design a runtime system which will compose that program into just the forwarding rules on the switch. So all the switches do is, all that the switch does is some sort of data plane functionality. Let me tell you what it actually does. So in some sense, we are taking the intelligence away from the switches into the controller, and the switches become sort of dumb. All they do is packet forwarding, but it is still fast because it's not doing any control plane stuff. So what exactly does the switch does the switch do? So all that the switch has is a table like this. Now, so this table is pretty much like a routing table, but you have some new fields. But the important thing to see is that each rule looks like this. That is, if the headers of a packet match this pattern, then you do this action. Right? You either forward it on some port, or you drop that packet, or you send it to a controller. Right? You have a certain set of actions that you can do if the packet matches the pattern. That's it. That is all the switch does. Nothing else. So it is pretty much. So this specification is called the Openflow specification. I don't know if you've heard of Openflow. So that is standard that has recently been agreed upon by all the major networking companies. Let me talk about the industry interest in this. So this is propaganda stuff. So the Open Networking Foundation, the foundation that has sort of agreed upon this Openflow specification, and you get all these new versions of Openflow coming out. So what that means is that any of these companies can write a controller or their own network application, and they'll be able to talk to any SDN network. Because an SDN network is going to have, let's say, Openflow switches, and the switches, all these switches have a certain interface called the Openflow interface, which is nothing but the set of rules that I just shown. And any of these companies can write an application which can talk to this network through this interface. So that is, and as I was trying to say, this is not sort of appending the network in a wishful manner. This is not some theoretical interest. This is the entire industry is looking at. Of course, not Cisco and Juniper. You don't see them because they make money out of these boxes. But the actual the guys who run the networks have faced lots of problems with having such vendor-specific stuff. So they want a generic, you can think of these Openflow switches as sort of the x86 architecture of some sort, which is very basic, and you're going to program that architecture. Okay, and a lot of new applications. Well, in some sense, these are old applications which you can write in the traditional network, but you write them pretty much on a single box. But now you write these applications in a piece of software on this central box, in the centralized controller, and that is compiled into Openflow rules for the switches. And there are also some real world deployments that we have seen recently. I don't have time to go into them, but there is a lot of excitement in the startup area as well. Nicira, I don't know if you've heard, has been acquired by VMware recently for $1.2 billion. And all it does is, VM migration related stuff in the cloud using virtual switches. So all these virtual switches are nothing but Openflow switches, but they do very flexible VM migration using software-defined networking. Okay, they have a virtual network which has the same architecture as this, and they use that to do some flexible VM migration. Please look it up. You will see that it's an exciting area. Okay, now that the propaganda is over, let's look at what the issues with SDN are, or why am I here. So the good thing about SDN is that now you have a centralized control over all the switches, and you have explicit control over the resources of the switches, and also the forwarding policy on the switches. But the bad thing is that it's a very low level interface to the switch. So what you're saying is that I'm going to interact with the switches in terms of pattern and action rules, which are very low level, in the sense that you're saying, if the packet matches this pattern, then it does this. I mean, packet can match millions of patterns. Right? How are you going to deal with that? And what you end up is having a very non-modular and non-compositional interface, because if you want to write a firewall and a load balancer, you cannot write them separately and say, I'm just going to import one into the other, something. You cannot do that if it's such a low level interface. That is, if you just write these programs in terms of rules. So what you want is a somewhat high level declarative interface, which sort of makes composition easy and also reasoning about programs. So what we want are some programming abstractions for the controller, and okay. So and then you should be able to write all these different applications, routing, policies, traffic monitoring, topology discovery, and so on. And okay, so let's talk about writing an application in this architecture. So what does it mean to program the network? That's the question that many of you will be asking, right? So how do you read a network? How do you, update the state of the network? How do you write to the network? Right? What does that mean? So let's look at a specific example. We're going to talk about a stateful firewall. This is a one-line explanation of what a stateful firewall is. We have a simple scenario where you have one switch which is connecting, let's say, the external world, the whole internet out there, with a certain, let's say, an enterprise network of some sort. That is, an internal network which you want to be protected from the external network, right? So what this switch does is that it will not allow any traffic from outside to the internal network unless someone has requested the traffic from inside. Okay? That's just what a stateful firewall is. So what this means is that the controller, or the switch, is going to be controlled by this controller, and the controller is going to remember the external host to which the requests were sent, so that the next time the reply comes, it allows that flow into the network. Okay? So let's see how this works. So initially, so what are these tables? So this is nothing but the flow table of the switch, which is controlled by the controller, and the table that you see is sort of the controller state, of the network that is maintained by the controller. And allow means it's going to remember all the external IP addresses that were contacted by the internal host. Okay. So initially you would need to say that any packet that comes in from the internal port should be forwarded to the external port, right? You don't want to block any of the traffic. You would want to send the request. So what that translates to on the switch is that you say that if the packet has the import as 2, which is the internal port, then you forward it on 1, right? That's the basic rule. Now let's see how this system evolves with this application. In such an application. So first a packet comes, which is addressed to the sectional host IP1 from the internal from this guy to the switch. Now what the switch does is it makes, so according to that rule, because it is on the input, it should be forwarded. But you don't want to just forward it, you also want to remember IP1, right? So you want to send that packet to the controller, right? So what this application should do is it should sort of make a copy of that packet if you want and send that to the controller and as well as forward it to the host. Now when you forward that packet to the controller updates the table with that IP address and now pushes an additional rule saying the next time you see a packet which is coming from IP1, you should forward it to the internal network because someone has talked to the host and you should allow the flow in the reverse direction. So that is sent to the switch and the switch adds that to its flow table. Right? So the next time the reply comes from that IP address, it goes directly to the internal host. Now what is happening so what has just happened in this entire process can be thought of as happening in sort of 3 phases. So first, what happens is a packet comes to the switch, right? And the controller is interested in that packet. So the packet is sent to the controller, and the controller sort of updates the network state that it maintains, and it pushes. After the update is done, it pushes additional rules, or you can say the forwarding policy, onto the switch. So this happens every time such a packet comes to the switch. So in some sense, you have a control loop going over these 3 phases. That is, set of interesting packets come in, and those packets are sent to the controller. The controller updates the state. That's the second phase. And the third phase is looking at the updated state, or in this case, the allow table. You push forwarding policy onto the switch. So, okay, so what I just did is that the next time the same packet is sent, it is not going to go to the controller, it is going to go directly here because you have already inferred the information you want from the packet. Right? So, so let's look at each one of the 3 components that I just described. The first component of the program is going to be the component where you describe what are the kinds of packets that you are interested in, that is the controller is interested in. So in this case, you are interested in all the packets that come on the internal port 2, and you are interested in the destination IP address of that packet. So what this guy says is that if you see on the left hand side, so if you see any packet on the internal port 2, then I want to look at the destination IP address of that packet, and that I'm going to log at the controller. Let's say using a temporary variable called scene, that I've seen this IP address in this phase. Okay, so you can write. So that is sort of the first phase where you tell the controller what is the flow that you're interested in, what is the flow of specific packet headers what are the specific packet headers that you're interested in. So a general rule will be like this. It says, I'm interested in those packets that have these constraints, and I'm specifically interested in these header values. H1, H2 are the header values, and X1, X2 are nothing but variables that describe the values of the headers. And I'm going to log them in a table at the controller. Okay, let's skip this. So the next phase is, now that you have a certain information about that packet, you're going to update the controller state. In this case, the controller state is nothing but the allow table that you see, right? So what you're going to do is you're going to add that scene, add that IP address to the allow table, right? this phase is nothing but a typical logic program, as some of you may know. So, for example, if you look at Datalog or Prolog or some such logic programming language, then it has inference rules, right? Set of inference rules. What an inference rule says is that if the facts on the left-hand side are true, then the fact on the right-hand side is derived in some sense and added to the state, right? Now, for our purpose, of course, however, we have a new construct, which is more like a temporal construct. What this does is that if the facts on the left-hand side are true now, then the fact on the right-hand side is going to be true now. That is, I'm going to add now, and it is going to persist in the next stage as well. Next stage is when the next packet comes, right? Now, all I'm describing is going to happen when a single packet comes. Now, all this happens, and then the next packet comes, and then again all these three components run. So it's sort of control, right? So so this rule says that this right-hand side is going to persist in the next stage as well. So that is what you see. What you see there is that the scene. So the allow is going to be updated now. Sorry, the scene that is the new IP address is going to be updated in the next. Sorry, is going to be added to the allow table, and the allow table is going to persist in the next stage as well. You may think this is, you can avoid this, but there are complicated examples where you do need this operator, because you may need some temporary variables, for this phase which you want to remove before you proceed to the next stage. So you need that. And the third is nothing but generating the policy from the updated state. Now, the first rule, this is for the firewall again, what you see on the graph. The first rule is a default rule, which is true anytime. So you're going to push that rule. It says that if you see a packet on the internal port, then you forward it. The second rule is going to be derived from the updated table, which is the allow table. So that says that if you see a new IP address in the allow table, then this is sort of the Openflow rule that you're going to push onto the switch. Okay? So this is going to be the Openflow rule. Now what this says is that if the pattern matches this, which says the source IP is this IP, then and it occurs on the external port, then you forward it onto the internal port with a certain priority. Now priority I didn't discuss, but if you have the same packet match multiple rules, then you disambiguate using this priority. That is, if the priority is higher, then that rule will be chosen. Okay? Because you can have multiple Openflow rules matching same packet. So, excuse me. So in general, you have something like this, which says, if a certain fact based on the updated state is true, then based on that fact, you have a new rule which is pushed onto the switch. Okay? So these are the three components. Now, that is what a stateful firewall application looks like in our language. Now, the red lines are just comments, they don't mean anything. Okay? So the first line is defining the flow that you're interested in. The next two lines are nothing but a logic program. That is a normal logic program, the normal logic inference. The last two lines are sort of defining the actual policy on the switch. So what I have just described is the syntax for a language called Plot, which is an event-driven logic programming language, but it's a forward-chaining logic programming language. If you don't know what that is, it's just that so forward-chaining means that you have a set of base facts and you keep on inferring new facts till you reach some convergence. That is, you cannot infer anymore. Okay. Now, this language again has three effects, as I just described. I'm not going to go into them again. But why logic programming, right? You may be thinking that you could have done it in some other way. Maybe, I don't know. But what you can easily see is that in a network, you deal with a lot of tables, and it becomes very intuitive if you can manipulate, these tables in logic program, using logic programming. And you can easily see that it is very intuitive to on all these three components. You have certain facts true on the left-hand side, and so you have a certain fact true because the facts on the left-hand side have just occurred. Or let's say a packet has occurred on the left-hand side, so you have a new fact, something of that sort. So in some sense, logic programming seems to be an intuitive way of looking at programming these tables of statistics, network statistics and network state. And the other reason, which I don't want to discuss much, is that you have a good number of tools available for incremental updates for state that is maintained by logic programming. Instead of saying that I'm going to erase my switch policy and I'm going to put everything again, you can just say, this is the delta chain that has occurred in the input, so this is the delta chain that I'm going to do to the policy. That's it. So, but in some sense, this is very much specific for SDN. So that's it. I'm not going to discuss this example. Okay, that's a long. But this is a learning switch example, which is like very compact. So the other interesting thing is that these programs are very compact. You'll be surprised to see how complicated the exact programs are in something like Knox or Beacon, which are like the most used programming interfaces for SDN right now. These are like really low level interfaces. But I'll just say that Flog is very heavily inspired by Frenetic, which is the base language that I was talking about. But Flog, in some sense, brings a very consistent feel to a Frenetic program. If you don't know what a Frenetic program is, just look it up. It is pretty much similar to what I just described, but it has three different languages for these three components that I described. But now we're trying to make all these three components look alike in some sense. That is, bringing a consistent view to the program. So that's it.
Questions? We have time for one or two questions while the next speaker sets up. Please go ahead.
In your list, the second is done with functional reactive programming, or it's a different approach?
Sorry, FML?
A functional packet stream processing language. So.
Yeah, it is functional reactive programming.
Okay.
Yeah.
And you want to put it with your logic language that describes the packet forwarding and this SQL-like language. So you can use all three of those in the same program, or how does it work?
So all these three are described. So all these three can be described using a logic programming-like approach. It's not just a logic program. I mean, if you see what I just described, it's not strictly a logic program, but it has slightly different semantics for some of the symbols that I introduced. So in some sense, it is different from logic programming, which is why you can put in all these three aspects. But it looks very similar to a logic program.
So it's designed to subsume all three aspects.
Okay.
How do you guys align your failure models in the sense that when you get failures coming in from actual physical devices on the network, how do they show up in your language, and how do you program and deal with it? Do you have things like exception models? Do you have things like, what's in your stack?
At the moment, we haven't honestly thought about it.
Okay.
But I believe Frenetic, however, has a way of dealing with some of the exceptions. That is, so Frenetic is based on this low level. Again, it sort of runs on the top of this low level interface called Knox, and Knox does have stuff related to so they are propagated up.
Okay.
Would you love to